everyone. I'm Pierre-Louis de Assis. I'm a professor at the University of Campinas in Brazil. And it's a pleasure to be here and talk to you about how much energy you need to program a photonic circuit to do arbitrary quantum state preparation. So just why use photonic quantum information processing? I mean, it has some advantages. One is that we have very long coherence times. We are essentially limited by the fact that eventually your photons get absorbed or scattered, so you lose your qubit. The processing speed is rather high, so you have about 800 picoseconds of transit time for your qubit to pass through a 2-qubit gate, because in photonic quantum information processing, your gates are physically implemented and static, and your qubits fly through them. It's the inverse picture of what you usually have in superconducting qubits, for instance, where you apply your gates. But there's a caveat that in our case, our 2-qubit gates are probabilistic. And so you have to repeat them a certain time, or at least part of the gate, and this increases your actual processing time. And they have less stringent cryogenic requirements and, let's say, simpler fabrication, because there are now foundries that can prepare these circuits for you, and you can operate at about 1 Kelvin instead of millikelvin range for your single photon sources and for detectors. So what would a full stack photonic computer look like? You need, of course, a classical layer to coordinate everything and control everything. You need your quantum light source, you need your programmable interferometer array, and your detectors. So I'm not going to evaluate the cost of these parts, because this is a cost that mainly depends on your time to solution. So how long does it take for you to actually get your solution? I'm more interested today in discussing this, which is a fixed cost that you pay when you program your photonic array. And what do I mean by a photonic array? I mean this. It's a square array. It was proposed, this architecture was proposed by Clements in 2016. It's a square array of Mach-Zehnder interferometers. Each Mach-Zehnder interferometer has 2 phase modulators that you can set with a voltage or with a current if you're using thermal modulators. And they are natively suited to work with qubits, because you can use the whole thing as a big qubit state preparator. But you can also program it to work with qubits. So this will be our standard hardware to calculate this cost, this energetic cost. It's this array of Mach-Zehders, and we are going to consider state-of-the-art electro-optical modulators, because nowadays, most people use thermal optical modulators, but these are incredibly inefficient. They're essentially resistive heaters, and so I want to keep my energy costs down, so we're going to explore these electro-optical modulators. They're essentially capacitors with material with a high electro-optical coefficient. So you apply a voltage to your capacitor, and it changes the refractive index for light passing through. It costs about, we're using the values from this reference, and it costs about 2 picojoule to implement a phase shift of pi, which is V pi is usually a figure of merit used for this kind of modulator. And you have to bear in mind that this modulator is 5 millimeters long. And if you want to make it shorter, you have to pay a price, because you have to apply a higher voltage. Okay, so this operates at a rather low voltage, but it's long. There is this trade-off. There is a constant, more or less constant product between constant voltage length product. And so energy is expanded when you program your array, but since it's a bank of capacitors, you're charging capacitors, and perhaps you can recover this energy later when you reprogram it or to do something else. And what task are we going to evaluate our performance with? We're going to check arbitrary quantum state preparation. which is well known to be a very hard task, even for a quantum processor, because it requires an exponential number of CNOT gates. It's the number of CNOT gates you need to perform is exponential in the number of qubits. And this is, has been known since 1995. But still, I mean, in many tasks, you will want to prepare a given state, or preparing this state is part of your algorithm, so it's an interesting task to evaluate. So for qubits, it's rather simple because, as I told you, the circuit will implement any unitary. You can program any unitary to it, and it will prepare the desired qubit state. But so it doesn't really scale very well for qubits. But so it will, since you have this scaling also for the CNOT gates in the qubit picture, it was not very clear to us which one would be more efficient, or if they would both be comparable in efficiency. So that's why we investigated qubits and qubits. So for qubits, we selected just 10 to the 4 Haar random matrices with D from 2 to 128. We performed the decomposition, and we calculated the energy cost of preparing that matrix given the phases we obtained from the Clemens decomposition. And then we fit this data to extrapolate it to a large number of, to a large dimension or a large number of equivalent qubits, let's say. But for qubits, the story is a bit different, okay? So each qubit is encoded in a single photon and 2 waveguides. So this is a dual rail encoding. And so in order to prepare an arbitrary multi-qubit state, we need to generate entanglement, so we need CNOT gates. And then the question becomes, how many CNOT gates do we need to prepare, to actually prepare this n-qubit quantum state? And so what we found in the work of Plesch and Bruckner was this algorithm, which was the most efficient we could find, but it uses some, let's say, long-range CNOTs. So we adapted it to use only nearest neighbor CNOT gates, because we don't want to have waveguide crossings in our photonic chip, because that introduces scattering, and if your photons get scattered, you essentially lose your qubit. Then, well, for the CNOTs, we tried 2 implementations. This one is by Ralph from 2002. It's a rather common implementation for small applications in photonic quantum computing, but the problem is that it has a fixed efficiency of 1/9, and so it's not scalable. So these were the energetic costs we got for each CNOT gate, so it's about 27 picojoule. If you use, so all these red circles, they indicate Mach-Zehnders that are set, they can either be set to the cross configuration or the bar configuration. The bar configuration is essentially the identity matrix, and the cross configuration means that you invert the outputs, okay? So it's a little bit more efficient to program in the cross configuration, but then your output gets, you need to do some relabeling. And then we investigated a bit the KLM CNOT gate, which is more complicated because it's built out of many blocks. It starts with this nonlinear sign shift, and with this you build a CNOT gate, which has a lower success probability than the Ralph gate. But the thing is that you can build up on it and get things that are that have a higher success rate. So this big circuit has a success probability of 1/4. But the problem is that you need 10 auxiliary photons, and you need a 24-port Mach-Zehnder array to implement it in a programmable photonic circuit, because we want to be able to compare qubits and qubits, right? And the energy cost that we found was about 170 picojoules, so it's already quite a lot, right? It's 100 times more than a single phase shift. And remember, the single phase shift is also a good figure of merit because the single qubit operations are essentially implemented by individual Mach-Zehnder interferometers. Okay. So, but how do we translate this to that Mach-Zehnder array? Well, it's rather complicated to keep track of where everything will go, so we needed, to do some creative labeling. I'll apologize for the horrible figure that will come in the next slide. So these boxes, these red boxes, are the nonlinear sign shifts. This is a CNOT gate, and this whole thing is actually, in a way, an error-corrected CNOT gate because it can detect photon loss. Okay, but it's still not the scalable CNOT gate that is promised in the KLM paper, because for that you need hundreds of qubits to make your quantum teleportation, which is the last step here, work nearly deterministically. Okay, so when we label everything and we translate, it becomes this huge thing, yeah. And so these boxes, these bluish gray boxes, are encoded here. The nonlinear sign shifts are here. These purple boxes indicate these other beam splitters. These are all beam splitters, okay? 50-50 beam splitters, but some with an inverse phase shift between reflected and transmitted branches. And all the rest of the circuit is just either cross or bar. It's for routing light from one block to the other. So there's a lot of empty space here that we need to program anyways. So it brings out the question, why use programmable circuits, right? Because for some problems, even in classical electronics, it's better to use an application-specific integrated circuit. It's more energy efficient. It might be even faster. And we will see when I show you the results that actually this will be true also for us. But in any case, we will need some degree of tunability, because even though you can have a foundry make it, or you can even, if you have a micro nano fabrication facility in your university or institution, you can fabricate these devices. They will have slight imperfections in the gap between waveguides, and this reflects to imperfections in your Mach-Zehnder array, which need to be compensated. So you need some degree of programmability to be able to get the circuit you want, right? So this is, these are our results. The purple line is the energetic cost of programming qubits. These are the costs, blue and green, for using the Rauf CNOT gate, and orange and red for the KLM CNOT gate. And so here we indicate the fully programmable and the fixed. The fixed is this quantum ASICs approach, where most of your circuit is let's say, fixed, and you just compensate for the slight imperfections. And you see that the quantum ASICs, the energetic cost is very, very low compared to the exponential growth you get in your programmable approach. And what was interesting, and shows that there was a non-trivial question in the beginning, is that actually if you're working with small dimensions, so up to dimension 64, if you're using 6 qubits or less, it might be more efficient for you to work with qubits to do quantum state preparation. Remember, I'm always talking here about arbitrary quantum state preparation as a task. It's more energetically efficient than if you want to use the qubits. Okay, but this is just up to dimension 8, right? It's not really that useful. That 10 to the 8, sorry. So let's extrapolate it a bit, and let's go to higher dimensions. You see, I put here 2 lines. The vertical line shows us the beginning of, let's say, the NISC region, where this corresponds to 50 qubits. Okay, so it's where you are no longer able to write down your quantum state on any currently available computer. But there is a red line here, and what does this red line mean? It's the total energy production of France in 2023. So, yes. So if you want to work with 50 qubits, you will basically need to store the whole energy production of France in your photonic circuit, which will be huge, by the way, because here we are talking about 10 to the 16 input ports. So it's, I'm not even here discussing the fact that there are other costs involved, for instance, in space or just the electronics needed to control all of this. But just to program it, it's going to be huge. It's still manageable if you want to do it in the KLM scheme. And remember, we're talking about those relatively cheaper KLM CNOT gates, which are not yet completely scalable because they only work 25% of the time. If you want the bigger ones, we haven't calculated the cost yet, but maybe later we could come with an answer for you on that. But anyways, this is about 100 qubits. So if you want to do, again, arbitrary quantum state preparation of more than 100 qubits, you again will hit this 1,000 terawatt hour barrier, which is essentially what a country, a big country in terms of energy production generates. So there's a problem, and here you see that the energetic cost for the fixed gates is very, very small. Again, because we're essentially not really programming them, we're just compensating for the imperfections. And the overhead of all the rest of the structure for the full stack calculation will be large because you need electronics to control, let's say, 10 to the 30 parameters, which is huge. So what about measurement-based quantum computation, right? Because then you don't need to build 10 to the 30 photonic gate chips. Yes, that's true, but you need to be constantly reprogramming your short chip. And that means that you need to operate in gigahertz frequencies if you want to get anything done in a reasonable time, like ending this presentation maybe. How long do I have?
A few minutes.
A few minutes, good. So you cannot use predefined gate circuits, so that shortcut is out of the question. And then you really have energy dissipation in your capacitors because they are no longer being quasi-statically charged. They are operating in an RF regime, so they will dissipate energy. And then comes the question, if you do measurement-based photonic quantum computation, I mean, is it really energy efficient to do something like this? Again, I'm talking about a very hard task because it scales exponentially with the number of qubits, right? So it sounds more depressing than it really is because this is really, I mean, one of the worst case scenarios in terms of energy consumption. So what about other tasks? Let's see if it's really, there is really no hope. And actually, there is. So if you want to break a 3,000-bit RSA encoding, which is currently the recommended key size, you will only need about 10 joule of energy to program the CNOT gates. Okay. So this is very feasible in comparing to preparing a 3,000 qubit arbitrary quantum state, right? Which again echoes that comment from the 1995 Barenko paper that, I mean, most of this huge Hilbert space is inaccessible simply because it's too expensive to get there, right? So what about take-home messages, right? Is that there is the energy is stored in the capacitors that you use to program your photonic circuit. So it might be recovered later or just shifted around as you reprogram the circuit. That specialist circuits that implement fixed CNOT gates have a much higher energy efficiency, and this can be explored. I mean, this can help bring out the advantages of doing photonic gate-based quantum computing. And that, at the same time, at least for now, the way we see it, measurement-based quantum computation, since it requires high-frequency reprogramming, you cannot circumvent this exponential cost in any way for the arbitrary quantum state preparation, and you always dissipate power. Even if you do, let's say, cheaper tasks, this power will always be dissipated instead of stored in your device. What about next steps? So, so calculate the cost of that nearly deterministic CNOT gate, but this is a huge task in itself. Do the full stack estimation, investigate other algorithms in real use applications, which will require thousands of logical qubits. So how much will it cost in a real case scenario? And well, investigate also classical noise, how it affects the quantum efficiency of these systems, because these electro-optical modulators, they can respond very quickly. They respond in the gigahertz range, so they are susceptible to gigahertz range classical electrical noise also. This is not really energy efficiency related, but anyways. So to acknowledge, funding this was done as part of this ongoing project to build a controller for our photonic chips and also these funding agencies. And last but not least, I must thank my wife and my kid who were okay with me taking a break from my summer holiday to come here and talk to you. Thank you.
Questions?
Thanks a lot for the very interesting talk. I'm not sure I understand the exponential scaling for MBQC though.
So
is it because it's arbitrary state preparation, or?
It's because it's arbitrary state preparation. It's because, okay, let me see which slide could be. I mean, it's essentially because the task requires an exponential number of CNOT gates. And in MBQC, this becomes an exponential number of measurement patterns that implement the CNOT gates, right? So it's...
Well, it's not particular to, I mean...
No. It's, I mean, if you did this calculation for a superconducting qubits, it would probably be maybe a bit less depressing or more depressing, I don't know. But it always blows up because of the task. But it was a useful task for us to see that, you know, in some regions, qubits can outperform qubits, for instance, and that having these ASICs, this ASICs approach is useful for photonic processing also.
And are you targeting to look at architectures like FBQC where you don't need very large chip, like, or
so
FBQC fusion-based computation for those?
We are. That's on our to-do list also. But I honestly have the feeling that it will be more or less the same issue as MBQC, because in the end they are rather similar, right?
Yeah, sure.
In terms of...
But you don't need like a chip with like 10 to the 30 parameters. I mean, okay, if you do want to do arbitrary state preparation, maybe, but probably it's not something you want to do anyway. Cool. Yeah. Cheers.
Yes. Very nice work. Did you look at generic tasks? Like, did you try to include at some point, maybe on the back of the envelope or something, like to include the cost of preparing the states and measuring the states, the things that are the beginning you said that you will not look? Did you try to get an estimation of, okay, what happens if you add the detectors and the sources? Just to get some more concrete numbers, let's say.
No, we didn't, but at some point, I have the impression that as you get, again, for this specific task, which is really the worst case scenario, but as you get in this region, I'm under the impression that this will be the dominant cost.
Right.
It starts very little, but it can quickly dominate your cost.
So
but it's honestly, I have to do even the back of the envelope calculation, because if you need 10 to the 30 detectors, everything becomes non-trivial, right? So
yeah.
Everything blows up in this case.
Indeed.
Did you account for the cooling of the system?
No, not
in
yet.
your estimates?
Not yet.
Because when I look at the numbers from PsyQuantum, it's huge. I mean,
yes.
I did the math. They need about 10 megawatt to cool 100 logical qubits system.
But what? Okay, so I mean,
not 10 megawatt for 100 logical qubits. That's the number.
Cooling. I'm not privy to everything they're doing now, but from what I've seen, what they're doing is a really, really brute force solution to the problem, which is they are using thermal optical modulators inside a liquid helium cryostat, which to me is a very bold approach, let's say, but if they can afford it, that's what they're doing. That's why we went with electro-optical modulators, because for EOMs, this is a fixed cost that it doesn't really matter how fast you program your chip. That's the amount of energy you spend. But in the case of thermo-optical modulators, then everything becomes a function of your time to solution, because the longer you need to run your gates, the longer you're leaving your resistors on, and the more power you dissipate.
And the paradox is they need to cool the SNSPDs in the same circuit, so they need to have a very low temperature to cool those SNSPDs, but they have these heating circuits, so it's contradictory to some extent.
I agree. And so the EOM approach, I think eventually it will become standard, but it's a very nascent technology, and still, the thing is, the thermo-optical modulators can be much shorter. Ours are like 200 microns long, and here you have 5 millimeters long to have about 4 volts of VPI. If you want to go to 200 microns long, you'll need about 100 volts per capacitor. And then you need to think about the power consumption of the amplifiers you will need to put this voltage into each capacitor. So, I mean, you shift your problem from one way to the other, and maybe it becomes less efficient.
Yeah, because you did account for the cost of the signal, but not the cost of generating the signal in your estimates. Did you account for both?
No.
Because you have a couple orders of magnitude usually between both.
Good point, and we should check this. But so far we're just really checking how much energy is stored in the
You'll see that with Jeremy Stevens' presentation tomorrow, because there's a big gap between generating the microwave that drives a qubit and then how it costs to.
Yeah. Thank you. Thank you very much.